Hello, everyone. I'm glad to be among the openers of this marvelous event, and I hope that you can see and hear me well. So when I was preparing this talk, I was informed that there are a lot of talks about what H3 is and how cool it is and how it was invented by Uber, and not really enough actual hands-on examples of how it could be useful and in which scenarios. And maybe when it's a good idea to use it, maybe when it's not. So today I'll talk a little bit about that. So some of you may know me. Hi, I'm Dorofei. You may know me as one of the people behind PostGIS. Also, it just happened that I've been using H3 for the last 5 years for geospatial analytics, and hopefully I can give you some taste of it. And currently I'm working at MauMap, where we help businesses to solve their geospatial problems with the UX analysis, data pipeline maintenance, and other consulting. I also love to take part in OpenAerialMap. I love to fly my drone. And recently, I remembered that I'm also radio engineer by training, and started taking part in the local radio mesh community. I also got a cat who is helping me today with this presentation. I'm living in Batumi, Georgia. If you don't know a lot about Georgia, the thing that you need to know as a geographer, that Georgia has mountains and also the Black Sea. Here you can see a photo from Gomez Mta, one of the nearby peaks. If you go to the other side of this marvelous view, you can find out that mountains are not only a touristic attraction, but also very fun for radio. Telecom towers are all around the mountains, and if you would love to put a small solar panel that powers LoRa repeater that provides the valley with a free off-grid text service. So it's powered by Meshtastic, which is off-grid decentralized network. Devices for Meshtastics are not really expensive. They're as low as $12. And what we learned while deploying it is that they are surprisingly capable. You can have a link on for 50. We got some links for 56 kilometers. It's not that much in urban settings, but there are more people, there is more noise, more volunteers, so there are more repeaters. So the mesh is still stable. It's also easy to go somewhere and put a solar-powered node somewhere so that it starts providing the coverage there. The largest problem is when you have decided actually getting there. Some people love to climb mountains, and they don't mind putting your whatever you want, whatever you ask them to put there. And yeah, having a free direct line to all the engineers in the area is a really nice perk. So today the whole talk will be about how do we decide where to put the nodes using PostGIS and H3. So H3, that is a perfect compromise between everything. It has almost equal edge length almost everywhere on the globe. The thing is optimized not for one single mathematical property, but actually for the sanity of the analyst. And that is the most important part to remember. If you're getting annoyed by H3, you're doing it wrong. Just to remind you about the compromises that it has to deal with. It may look that it's made of hexagons, but it's not really hexagons. It's not really hexagons on a sphere either. It's more like a D20 dice that is stretched out to be a spherical thing. And here is an illustration done by my colleague Nadia, who is also a contributor to H3PG, that she has done as part of 30-day map challenge, which is ongoing. I've got some more pictures. This picture is also from 30-day map challenge by my colleague Alexander. And you may have heard that H3 hexagons have the same area. Yes, in close proximity they do. Not really if you're taking the whole globe into account. It's pretty possible to find two cells of the same, of which one would be twice as large as another, on the same single resolution level. Still, it's got a lot of edge cases, but others be worse. If you ever have thought the thing tries to get inverted along the equator or across anti-meridian, you may be really happy with H3 because it is not a thing that happens in H3 unless you try to go from H3 to some other system, like a cylindrical globe. So when you want to work with H3 in Postgres, you need to install the corresponding set of extension. In my opinion, the best one is by Zacharias, and with to it every time we have an opportunity. So thanks for quick reviews. And yeah, every time you're dealing with H3, the very first thing that you need to compromise on is that you need to decide how much are you going to lose? How much certainty do you want to lose? For today's project, I think I'll be picking resolution 8. I have two favorite resolutions. Resolution 8. So if you want to have a map of everything on the planet, and you still want your laptop to be to have some RAM after that, you may want to pick resolution 8. 400-meter edge length means that you can walk from any point in the hexagon to another point, well, unless the thing that stops you. And yeah, that's a nice one. The other resolution that I'm working when resolution 8 is not good enough is resolution when you need a very specific building. It has closer to 30-meter edge length, and usually it means that the nearby streets are no longer getting rounded to the neighboring hexagons. So you can start using that for pathfinding around the block. Usually, if you need more detail than that, you're probably trying to use H3. If you have more detailed data than just a very specific building and you're trying to put it into H3, maybe reconsider, maybe either you don't need that precision, or maybe you really need to choose some other tool and it will help you better. And I hope it's clear why Heisenberg's uncertainty is blurry on this slide. So let's formalize the task. I would love to find locations for the network of radio repeaters in Georgia. I would love to add them one by one. So everyone should be growing the network towards some new populated area. As I mentioned, resolution of 8 is probably going to be okay for this. For the purpose of this demo, we are going to assume that 60-kilometer links are stable. In practice, they are not, but that's probably for a longer talk. And DEM will be enough. As you've seen on my photo, most of the obstructions are going to be just the mountains. It's not going to be an urban terrain. I also would love to go there by car. I don't really want to climb a mountain if there isn't a road going there already. I also have some sites installed already, and I don't really, if there's going to be some heuristic, I don't want it to contradict what I observe. If some sites can see one another, they should be seeing one another in whatever model we provide. So that's an important aspect. Whenever you are dealing with any kind of model, you need to find something that you want to keep working in this model. In this example, there is a global meshtastic map. It doesn't show all of the repeaters. It only shows the devices that whenever owner went through the inconvenience of connecting the device to the internet. And you can see 3 cities here. you can see Batumi, you can see Poti, and you can also see Tbilisi. So Batumi and Poti have a really nice radio link between them. There is just sea in the middle. And there is a long way until we are able to connect to Tbilisi directly. So what kind of data we will need to collect to perform this site selection process? I think we need to start, well, with the ground truth data. Elevation raster, of course, we'll need. Roads data, because I want to park a car somewhere. Country boundary. I really, really want to only connect Georgia, because in the neighboring countries, radio rules are vastly different, and it's not going to be helpful to connect the meshes across the boundary this time. And population density is always useful whenever you're trying to service people, because you want to provide service to the people and not to the land. I picked those data sets so that each of them is a different data type. So the points, the nodes are points, the raster is raster, roads are probably lines, country boundary is gonna be a polygon, and population is gonna come as already as a processed H3 grid. It may take some time for some people to cross-reference all this. It usually, because whenever you want to join raster to points or to lines, it usually takes some creativity to perform it. And this time I'll show you how H3 simplifies all that. So where we will take all that. The points, I've sketched the points in geojson.io. For elevation raster, since we're dealing with 400-meter global grid, I'm gonna take gap column. And for roads and boundaries, I'm gonna take OpenStreetMap. Population density, I'll take contour population, which is a data set I've been working on for the last couple of years. So when you want to convert the GeoJSON points to H3, it's pretty simple. You first need to get the GeoJSON into Postgres. And as a second step, you would probably want to aggregate it. There are several different things to be aware of. It could be that multiple points will land on a single H3 cell. It's really an inconvenience if you get a data set that has duplicated H3 index in it. You need to decide what you want to do here. Here, I'm just merging those together and collecting their geometry together and grouping by the H3 index. So afterwards, I will be able to treat H3 index as a primary key. We also found it useful to add the geometry column, because the fact that you have H3 doesn't stop you from still working with the same data set with PostGIS. And I'll show you how exactly to do this later. QGIS unfortunately doesn't yet show H3 as is, so whenever you want to visualize something, you will have to deal with that and add the H3 column, add the geometry column. And another important thing is that we settled on, internally we had some debates, and we settled on this naming convention. So whenever we have a table that is not an original table, not an input table, but the processed H3 table, we add a postfix H3. So it is really clear that it's not going to be a geometry, it's not going to be the source geometry. It's going to be H3 cells primarily. And whenever you know the resolution, you want to have the resolution also marked in the table name. We usually put it under underscore R and the number of resolution, so R8 or R11. Why is it useful? Because sometimes you want to join some tables that are on different resolutions, and they have no matching primary keys. So you think you're creating a join, and the result of that join is an empty table. To avoid that, it's really better to see that you're trying to merge and join something that is not compatible before you try to execute it. I love the Osmium tool. It really gets OpenStreetMap into database and gets out of the way. Later today, there should be a presentation from Jochen Topf, who is the author of Osmium. And he will tell you more about the other tool, OSM2PGSQL, which is a more powerful thing. You may want to learn it if you're okay with learning an extra programming language to deal with the import. If you prefer to deal with everything in SQL, just steal this, and it's gonna be okay, and it's gonna get you really, really far. The other thing that I want to mention is that all the things I'm showing in the presentation today, they will be shared as a repository, and you can reproduce that locally, open your ticket, ask your questions directly, reviewing the actual code that's getting executed. So you will have a source to copy this from. When I'm extracting the boundaries of Georgia, I'm extracting two of them. I'm extracting the actual boundary of Georgia, which is the administrative boundary of level 2, where the name is Georgia. And then I'm building a convex hull of it. Why is it useful? It really helps because radio is not following boundaries. Radio just goes directly. So if you ever need to connect this spot and this spot, the radio wave will go directly. And in order to check whether they are connected and there is no obstacles, you will need to have the information about the elevation in those areas too. Speaking of elevation, I mentioned GAPCO. Funnily enough, GAPCO is meant to be an oceanographic data set. It's supposed to be the data set of depths. But funnily enough, it provides a global grid of elevations at 15 arc-second, which is roughly 460 meters, which is roughly the resolution 8 of H3. So I think it's a perfect data set to use whenever you need the elevation. And the elevation has to be at resolution 8. So in order to import it, you just take the normal raster to PGSQL command. Don't forget -t auto in order to tile it so that you don't get one single multi-gigabyte row in the table. Postgres is really not happy when you're dealing with it this way. And then we are processing it using our templated script. Here you can see that we're taking the input table of GAPCO elevation, the output table, and the aggregation function that we're using is average. We want to receive the average of the cells if there are multiple cells going into one single H3 cell. We also want to clip it using the convex hull of Georgia. The templated script is also not that hard. It's just that it comes up over and over and over whenever you're dealing with raster. The trick here is that you can join pixels as centroids, which converts your pixels of the rasters into points. And we already know how to deal with points. This is not the only way to convert H3 into raster. If your H3 cells are significantly larger than the pixels of the raster, you may want to rasterize the hexagons and then deal with that as normal zonal statistics. Hooray, we got GAPCO in the database. Now we want to have roads. I want to pick all the roads for motor vehicles. So I'm filtering them to normal SQL filters. Then roads are lines, and the lines are not points. How do we make them more point-like? So in this example, we are first taking the lines of whatever length they come in and make sure that they are split into the segments of no more than 200 meters. Then we dump every segment as a separate pair of points, as a separate small line string, and then take the start point of it. What you get as a result is a point that is guaranteed to touch every single H3 cell on the way of that line, and that makes sure that every cell is going to be touched. So, hooray, we got the rows as H3 cells. If you want to import population data in H3, you can just import it, and funnily enough, it's already in H3. You don't need to do extra processing. Now, let's combine everything. This is where things get more complicated for GIS specialists and a lot easier for normal database engineers. H3 index acts as a geographical primary key. It allows you to join various datasets together without any complex calculations by just using the equality on the H3 field. For many beginners and many data engineers who are not GIS specialists, that's going to be a life-changing thing because what you learned in the university still holds up. You still can get the geometries, but it's also okay to avoid to just drop them and not use them if you don't want to show your table in QGIS and you have your data pipeline. You've got terabytes of data and you don't really want to pollute the database with that. The next thing that we need is a line of sight function. There is a long function. I don't think I really got enough time on this presentation to go through all of it, but the key part of it is that if the elevation of the terrain is above the line of sight is blocked. So you can have a look at the longer version of this in the shared repository. But what we got as a result is that the nodes that about which we know that they are connecting together, they are indeed connecting. We got connection between Batumi and Poti. We got connection between Poti and Gomez and Tang. And connection with Tbilisi correctly is not existent. So unit test passed. The next thing to perform is to run the greedy loop to pick the direction of growth. So you start with refreshing all the hexagons and marking every hexagon that has reception, that has 60 kilometers, has a tower that is visible within 60 kilometers. You check that you can actually place the towers nearby that the previous candidates, and then you want to score the candidates. In order to score the candidates, you sum all the population that is visible from every candidate hexagon that was not yet covered by the other part of geometry, by the other towers. Afterwards, you can have the top element of that. You can mark it as a best location. You can mark it as a next location to install the tower, and continue the loop. The result, here is the result of the running this algorithm. So here you can see the LoRa mesh for all of Georgia that could be installed within 70 nodes that actually follows both roads and terrain. If you want to learn more, here are some interesting links. The first one is a repository with the full experiment. Second one is documentation on how to write such repositories. And thank you all. Let's be in touch.